So you will find a set of notes in Schoology, Lewis structures, formal charge, resonance, and exceptions. And so we'll run through this. Again, most of this should be review from last year in Honors Chem. All right, so we're going to be talking about Lewis structures for covalent bonds. And basically, they're representations of molecules showing all the electrons bonding and non-bonding that are involved in the molecule. So here's hydrogen. Here's 2 electrons that are involved in a bond. Here's chlorine. Here's 2 electrons that are involved in a bond. And 6 electrons on each that are not involved in bonding. And those are our valence electrons. So when we write Lewis structures, okay, very first thing I'm going to do is I am going to find the sum of valence electrons of all the atoms in the ion or molecule. If what we're talking about is a polyatomic ion that's an anion, we're going to add electrons, however many is in the charge. If it's a cation, we're going to subtract electrons to match the charge. Okay, so in terms of valence electrons, if I look at phosphorus, phosphorus has 5 valence electrons. Chlorine has 7. We have 3 chlorine atoms, and so that's going to be times 3. So this is 21 plus 5, so altogether I've got 26 valence electrons to work with. Then I'm going to go ahead and figure out which atom in my compound is the least electronegative. The least electronegative that isn't hydrogen. So in the cases of PCl3, if I use my trends, I will see that P is less electronegative than chlorine. So I'm going to go ahead and I'm going to put that in as my central atom. Okay. Then I'm going to go ahead and connect all the rest of the elements, the other 3 chlorines, to it by using single bonds. Okay, each of those counts as 2 electrons. So 2, 2, and 2. So we started with 26, and we just used up 6 valence electrons. So that's going to leave me with 20 valence electrons left over. Okay. Then I'm going to go ahead and I'm going to fill the octets of the outer atoms. Okay, so we're trying to make everything obey the octet rule. So the bond counts as 2, and then we go 3, 4, 5, 6, 7, 8. To fill out that chlorine, 1, 2, 3, 4, 5, 6, and 2 in the bond for that chlorine, 1, 2, 3, 4, 5, 6, and 2 in the bond for that chlorine. Okay, so we take the outer atoms and we fill up their octets. Okay, so we had, after we took away the 6 for the bonds, so we had 26 minus 6, which gave us 20, and we've just gone ahead and we've used up 18 more electrons, which leaves us with 2 valence electrons left. Then I go ahead and I fill the octet of the central atom. Okay, so I add 2 electrons onto that phosphorus right there. Okay, that gives it 2, 4, 6, plus 2 more is 8. We're down to 2 valence electrons. We get rid of 2, and we are at 0. All right, so that's what happens if everything works out perfectly. But sometimes you will run out of electrons before the central atom has an octet. In this particular case, we're going to go ahead and we've got our hydrogen. Now, hydrogen, remember, is always okay with just having 2 electrons around it because it's in that first energy level, so we're good there. So we've used, we've got 2 valence electrons there, plus 2 in the bond, plus another 2 in this bond, plus we've filled the octet of the nitrogen on the outside. Okay, so is everybody obeying the octet rule? 2, 8, but the carbon only has 4 valence electrons in it. So we have to go ahead and we have to form multiple bonds until that carbon does. So we're going to take some electrons and we're going to move them around to form more bonds. So I'm going to take, the only place that I have some electrons to donate is on the nitrogen. So we're going to add that in. Okay, that gives me 3 bonds. Gets rid of these ones up here. The nitrogen still has 8. Now the carbon has 6. So I'm going to do it again. 2 more. We're going to share those into the middle. Okay, and if I do that, now the nitrogen still has 2, 4, 6, plus 2 more is 8, and the carbon has 8 right now, and we end up with the structure. In this case, it has a triple bond in it. Okay. Why is the number of bonds important? Well, because in general, the greater number of bonds between 2 alike atoms, the shorter the distance between them. Okay, so you can think of it as like a tighter and tighter rubber band. If I only have a single bond, it's pulling those atoms together, but if I have a triple bond, it pulls them together even more, and you end up with a shorter bond length. All right, so in general, then, that's how we write Lewis structures. But sometimes when we write Lewis structures, we end up with more than one Lewis structure, which is valid, right? You end up with a situation where, depending upon how you put electrons in, you might have more than one structure that fulfills the octet rules and follows the rules we just talked about to put this together. So when that's the case, we have to think about what we call formal charge. Okay, so we're going to go ahead and we're going to assign some formal charges. So basically what we're going to do is for each atom in a structure, we're going to count the electrons in lone pairs and half the electrons it shares with other atoms. Okay, then we're going to add up the number of valence electrons it brought to the party. Okay, the difference between them is the formal charge. So if we look here, we've got two structures for carbon dioxide which are valid, okay, which both meet the octet rule and use the right number of valence electrons. So which one is going to be better? Well, again, formal charge is used for that. So let's go through each molecule and figure things out. So if I start with this oxygen, okay, we know that oxygen comes with 6 valence electrons, okay? If I, in the structure, check it out, I see that we have 1, 2, 3, 4 electrons plus half of each of these bonds, so that's 2 more, so that's 6 electrons altogether. If I subtract those, that means that on that atom, there's a formal charge of 0. Carbon, we know that carbons come with 4 valence electrons to begin with. In this structure, we have 1, 2, 3, 4 electrons assigned to carbon, half of each of the bonds. So that's, once again, 4 electrons. So we end up with a formal charge of 0 on that. The last oxygen, we deal with the same way as the first oxygen. So it brought 6 valence electrons to the party, and around it right now we have 1, 2, 3, 4, plus half of each bond gives me 6. So formal charge of 0. Okay. If I look at my other structure, we know that oxygen brings 6 valence electrons to the party, and we go ahead and we add up the electrons around it. 1, 2, 3, 4, 5, 6, plus half the bond is 7. It has a formal charge of -1. Carbon brings 4 to the party. It has half of each of the bonds that are with it, so it has 4, so it has a formal charge of 0. The oxygen on this side comes with 6, and right now it has 1, 2, plus half of each of the bonds assigned to it, so 5 electrons overall, and it has a formal charge of +1. So how is that helpful? Well, the best Lewis structure is the one with the fewest charges. So the more zeros you have in terms of formal charge, the better the Lewis structure. Okay. The second thing is if those are all equal, it's going to put a negative charge on the most electronegative atom. Okay. So on your left side, what I'd like you to do is I'd like you to go ahead and take these 3 structures. They've got their formal charges assigned to them in red, and I want you to tell me which one is the best Lewis structure, which one is the middle, which one is the worst. Come back when you're done. All right, so should be pretty easy to figure out which one is the worst, because the first one we look at is the one with the fewest charges. These both have 2 zeros and a -1, so that's good. This one has a -2 and a +1, so this one is definitely the worst. Okay. Then I go ahead and look at these two. Their formal charges are the same, so we want to find a negative formal charge on the most electronegative atom. So the question is, what's more electronegative, the nitrogen or the oxygen? Knowing our periodic trends, we should recognize that the oxygen is the more electronegative of the two, and so this is the best structure, and that one's a close second. The other thing that happens in Lewis structures is sometimes there's more than one valid way of drawing the exact same Lewis structure. So if we look at this structure for ozone, we see that there's a double bond on one side of it and a single bond on the other side of it. However, if we go ahead and we do some spectroscopy, we can find out that the actual length of the 2 bonds that are over here is the exact same, which is not what we'd expect, because we said a little bit earlier that having more bonds typically gives you a shorter distance and less bonds would give you a longer distance. Well, that's not what we see in reality. There's a conflict here. And so the way we solve that conflict is with the idea of resonance. In resonance, you have two different Lewis structures that are completely equivalent for the same molecule. Same in formal charge, same in electronegativity, all of those things. They're exactly the same. Okay, so in this case, it would be putting the double bond on one side or putting it on the other side. Those structures are the exact same. That's called a resonant structure because they are both equal. And in reality, the real structure is actually a hybrid of them both. Okay, so it's not like the double bond flips back and forth. It's more like there's 1.5 bonds on each side. And that then makes the bond lengths a hybrid as well, which would explain why they are the same on both sides, same distance on both sides. Okay. In reality, the electrons that form the second bond aren't actually assigned to one atom or another. They actually move around amongst the two bonds that are listed here. Okay, so they are not localized, they are delocalized. Okay, so they do not just sit between two atoms, they actually can move between several atoms. And we'll talk a little bit later in this unit about why they can do that, but we're just getting started with that, so just so we can understand the difference between a localized atom and a localized electron and a delocalized electron. Okay. All right. As a point, I do want you to know one common resonant molecule, and that's benzene. Okay, benzene comes in a ring structure that looks like this, where it's a carbon ring of 6 carbons with alternating single and double bonds. Okay, oftentimes in chemistry, you see it represented like this or like that, all right, to signify the delocalized electrons in the ring. Okay, so in other words, again, it's not a single bond and a double bond and a single double bond. It's more like 1.5 bonds all the way around because the electrons are free to move between the different atoms. All right, just like almost everything else in chemistry, we do have exceptions to the octet rule. There are 3 types of ions or molecules that do not follow the octet rule. 1, ions or molecules with an odd number of electrons. We'll get to those in a little bit. Ions or molecules with less than 8 electrons. We'll get to those in a little bit. And ions or molecules with more than 8 valence electrons, an expanded octet, which will happen when you end up with some things that have D sublevels. Okay? So, some exceptions I want you to know. Beryllium can be fine with 2 bonds instead of 4. Boron can be good with 3 bonds instead of 4. Phosphorus, 5 bonds instead of 4. Sulfur, 6 bonds instead of 4. And xenon are also 6 bonds instead of 4. Now, these are can, not must exceptions. So 5 or 4, 6 or 4, 6 or 4, 2 or 4, 3 or 4. Right, so let's go through each exception case. Okay, first one is an odd number of electrons. Okay, so if we look at this, odd numbers of electrons are rare. They're usually often quite unstable and reactive. If there's a free electron just sitting out there, something else wants to grab it. And so we refer to these as radicals. All right. So here are 2 structures for nitrogen monoxide. What I want you to do, quick left side question, which NO structure is dominant and why? Go ahead and take a look and think about it. Come back when you're done. If you need a clue, think about formal charge. Come back when you're done. All right, so nitrogen brings 5 valence electrons to party. Oxygen brings 6. Okay. In each of these structures, here's the nitrogen. It has 1, 2, 3, 4, and half the bonds is 5. So it has a formal charge of 0. Oxygen likewise, 1, 2, 3, 4. Half the bonds is 6, which gives me a formal charge of 0. Over here, the nitrogen has 1, 2, 3, 4. Half the bonds is 6, which gives me a formal charge of -1. The oxygen has 1, 2, 3, and half the bonds is 5, a formal charge of +1. Therefore, that is the structure that dominates. Second exception is atoms that have less than 8 electrons. This happens in the first period and the second period of the periodic table, basically the first like 5 atoms that we have. So again, in the first period, hydrogen and helium, they have 2 valence electrons. They only make 1 bond. Okay, they only make 1 bond. And again, that's because in that first energy level, we only have 1 s1 and 1 s2. So therefore, there are only 1 or 2 valence electrons available to them. In the second period, boron and beryllium are most commonly the ones that have less than 8 electrons because, again, once we get up there, we get 2s1, 2s2, and if we're dropping down electrons there, those are the ones that get disappeared, and so we drop back down to a place where we only have 2 valence electrons. Okay, so let's consider boron for a second. Okay, so if we fill boron with an octet, if we put 8 around it, it actually ends up putting a negative formal charge on the boron and positive on the fluorine. Okay, that is unfavorable. Why? Because again, we have formal charges on the atoms. There is another structure that works for us, and that other structure that works for us is putting a single bond around the boron and filling the octet of all of the fluorines. This leaves everything with a formal charge of 0 because boron only brings 3 valence electrons to the party, and now we've got 3 valence electrons that are assigned to it. So that leaves boron with only 6 valence electrons, and that in this particular case is favorable. We also know that this is true because it's consistent with the way that boron bonds with other things, consistent with that chemical behavior that we actually see happen. The third exception is when you have more than an octet of valence electrons. These we refer to as being hypervalent. It happens when you have period 3 atoms that are central atoms, period 3 and higher, where that element is the central atom. And it happens for a number of reasons. One, once you get there, we know that our atoms are getting bigger, which means that the electrons are farther away from each other, which means that there's more space for us to put electrons together and share them, creating more than 4 bonds. They don't get too repulsive to keep that happening. The other thing, a minor factor in this, is that you can actually use the d orbitals that are in period 3 and below to go ahead, and higher, to go ahead and use those to actually do bonding in. The 2 that we most commonly discuss here, phosphorus. Okay, phosphorus comes with 5 valence electrons, and it can actually make a bond with each of those. All right, so we go ahead and we can bond out with that and have actually 5 bonds or 10 valence electrons altogether with the phosphorus. Sulfur comes with 6 valence electrons, and so likewise it can make 6 bonds. Let's guess 5. Smaller outside atoms, okay, the ones that go on the outside, it's most common that you have fluorine, chlorine, and oxygen on the outside of these structures, again, because these are small atoms, and so therefore the electrons don't get in the way and get them repelling all over the place. So why can exceptions exist? Well, we can think of this in terms of the exceptions will oftentimes give us better Lewis structures. All right, so even though we can draw Lewis structures for the phosphate ion, for example, with P in the middle with only 8 electrons around the central phosphorus, the better structure puts a double bond in there. Well, why? Well, in this case, if we put single bonds all the way around it, we end up with 5 formal charges. Whereas if we put a double bond in there and use that expanded octet, we only end up with 3. Okay? So when the central atom is on the 3rd row or below and expanding the octet eliminates some formal charges, do it. Go ahead and see, can we get rid of some more of those formal charges?